Hello, this is the first of the linear programming series for OCR Discrete Further Maths and covers the formulation of linear programming problems. Decision-making processes have to be carried out in many areas of life, and mathematical models can be used to turn the requirements, constraints and objectives of a project into algebraic equations. So linear programming is the process of solving these equations by searching for an optimal solution. Linear programming methods are some of the most widely used methods employed to solve management and economic problems, so they can be applied to a variety of contexts with potentially enormous savings in money and resources. First, we are going to look at how to turn problems stated in words into algebraic equations. Linear programming problems will involve several decision variables that are usually quantities of the different items that are to be made. And the aim is to determine the optimal values of these decision variables. Real problems generally involve a number of constraints or limitations that are written as linear inequalities. There is typically a quantity to maximize or minimize, for example profit or waste, and this is called optimization. An objective function is used to define that quantity that we want to maximize or minimize. Here's a typical linear programming problem. A company makes two types of box, each requiring the same amount of material. And to make either box, they both go through a folding machine and a stapling machine. We're given the following information: that type A boxes require 4 seconds on the folding machine and 6 seconds on the stapling machine, whilst type B boxes require only 2 seconds on the folding machine but 7 seconds on the stapling machine. Each machine is available for 1 hour, and there is a profit of 40 pence per box on type A boxes and 30 pence per box on type B boxes. So the question would be, how many of each type of box should be made to maximize the profit? Let's consider the assumptions made in the question. Well, firstly, we've assumed that there is sufficient demand for either type of box, and that the staff can all make either type of box. We've also perhaps assumed that zero time between boxes on the machines, so we only have to consider the amount of time given in the statements above. If we tabulate these statements, we can make it easier to then produce the mathematical or algebraic inequalities or expression from that table. Here you can see that we have a column for the type of box, but then the last row also states the total time. So for the type A box, we reflect the 4 seconds on the folding machine and the 6 seconds on the stapling machine, taken from the first statement. The second statement populates the second row, with type B requiring 2 seconds on the folding and 7 seconds on the stapling. We can see that the fact that each machine is available for 1 hour has been written in seconds here. It's quite important to always check the time units. And then there is another column for the profit. This is given in pence, in accordance with that last statement. Using this table then helps us to formulate the problem. So we need 3 aspects to formulate the decision variables. Well, we've let x equal the number of type A box that we're going to make, and y to equal the number of type B box that we're going to make. Including the words number of when you define the decision variables is really important. X does not equal type A and y does not equal type B. They equal the number of that you are going to make. So that's for decision variables. The objective function was that we wanted to maximize the profit, and we can see that the profit will be 40 pence on each of type A box. So if x equals the number you're going to make, that will be 40x. Similarly, adding 30y. And we need to write the word maximise in front of that if we're looking to maximise. We'll also look at minimise problems later on. We also then need to define the constraints, and we can do this by looking down the columns. So we look down and say that the number of boxes for type A, x, times 4, so 4x, plus 2y has to be less than or equal to 3,600 seconds. We've simplified the coefficient, so as a common factor of 2, so that becomes 2x plus y is less than or equal to 1800. This constraint reflects the limitations on the use of a folding machine. Similarly, the limitations or constraint on the use of a stapling machine is that, and this should read 6 from the table, 6x plus 7y is less than or equal to 3,600, again taken from that column for the stapling machine in the table. We also need to note that the number of boxes made has to be greater than or equal to 0. You cannot have a negative number of boxes made. In addition, there may or may not be a statement to the effect that you can only make whole boxes, so x and y must be integer. Once the decision variables, the objective function, and all the constraints are clearly stated, the LP problem is then considered formulated. In the previous example, the constraints were pretty straightforward. But sometimes these may not be as easy for someone, particularly if you speak English as a second language, to work out. Here are some examples of the type of language that may be used. For example, fewer than, must not be more than, a minimum of, cannot be more than, no more than, must not be less, must not exceed, and so on. Let's see which of these boxes would actually mean constraint of less than 25. Well, fewer than would be, so that would be a box A. Box B must not be more than, would be less than or equal to. So you can see that you have to read it very carefully. For C, a minimum of 25 would be greater than or equal. Likewise for D, it cannot be more than 25, would mean that it has to be less than or equal to 25. Up to 25 would be that 25 was greater. Exceeds 25 would be that statement there. More than 25, the same. No more than 25 would be less than or equal to. At most 25, less than 25, must not be less than 25, must not exceed 25, a maximum of 25, only 25 are available, so again that's less than or equal to 25, or at least 25. There. You take some time to look at the different terms and language used in questions and make sure that you are familiar with writing the inequalities. A couple of even more difficult constraints are shown in this slide here. Well, how would you write these as inequalities? So let's think about the example where x is the number of milk chocolates and y is the number of dark chocolates. If there must be at least twice as many dark chocolates as milk chocolates, then which way round is it in terms of where the 2 goes? If you had the same number of chocolates, then x would equal y. However, if you have at least twice as many dark chocolates as milk chocolates, then you would have to have 2x being less than or equal to y. If the dark chocolates must be less than 40% of the total number of chocolates, what we are saying is that 40 over 100 x plus y, which is the total number, must be greater than y. So, y being the number of dark chocolates must be less than 40% of the total x plus y. If you rearrange that, and we can use some decimals to do this, we can just say 0.4x plus 0.4y has got to be greater than y, and that boils down with then some multiplication to tidy up the numbers to 2x needs to be greater than 3y, or in other words, y is less than 2/3 of x. So again, it's worth you reading through as many old questions as you can and familiarise yourself with translating the constraints from word statements to mathematical inequalities. In the next session, 1.2, we will consider finding a graphical solution using the vertex method.